So here's just a couple of slides on the whole idea of filters and band passes. We'll go through this again later, and this series of slides is actually an excerpt from a much longer talk, part of which is already a Nighthart movie, and part of which we'll go through when you come in the summer, but this is just the critical bits on the whole filter band passes concept. So the whole idea is sort of like, remember those old-fashioned 3D glasses where you have one eye that's a red a piece of plastic and the other side is a blue piece of plastic. You can get those kinds of colored plastics for theater, for example. They're called gels. You can put them in front of spotlights to make colored lights. So if you can imagine looking at the world through one of those pieces of plastic, this is a really imperfect PowerPoint approximation of how you do this, but the whole idea is that you're looking at a multicolor picture, but you're looking at it through a red filter. You're looking at it through, for example, a red gel, and then the world looks very different when you're looking at just the red light. So a perfect filter would let in literally just the red light. So if you have here transmission as a function of wavelength, it would let no blue, green, yellow, or orange light in, and will just let red light in and not anything longer. In reality, it's much more complicated. This is a real red filter transmission curve. It's R band, Johnson R, maybe Cousins R, I don't know. It's from Kit Peak. And we've got transmission as a function of wavelength here. So it's not, so this right here is called a top hat function for sort of obvious reasons because it looks like a top hat. This is not a top hat function. It's trying, but it's not. So you see it lets no light in until about 5,600 angstroms, and then the transmission rises rapidly. But it rises over 200 angstroms, and the maximum efficiency of transmission is only 90%. And over this range of wavelengths, you can see there's bumps and wiggles, and then at around 7,000 angstroms, it starts to fall. But again, it doesn't do so in an ideal fashion. In fact, and it has this rather long red tail, where it's letting light in even at 8,000 angstroms, a whole 1,000 angstroms longer than where that filter is really supposed to cut off. And so what this means is if you have a source that puts out most of its light in near 8,000 angstroms, but not at the shorter wavelengths, you can, because of this red leak, get a much brighter measurement of the total flux from the object than you would expect if it didn't have that light leak. So here's examples of several more filter band passes. Again, it's transmission as a function of wavelength, this time in nanometers. So we have Johnson, U, B, V, R, and I. Those might be Cousins R and I, or it might be Johnson. I think it's Johnson R. I think it's Cousins I. So you see that they are rather far from being top hat functions. They're not even symmetrical. The U is pretty symmetrical. The B is a little bit more asymmetrical. V is asymmetrical. R is very asymmetrical. And I'm pretty sure that's Cousins I because it is much closer to a top hat. There's also Sloan G and Sloan R and Sloan Z in here. I found this picture a long time ago, and I subsequently, when I've tried to go back and find it again, I've found less of a large collection of filters on one page, but I'm not so sure that the shapes are completely right. But the idea is correct. A clear filter lets all the light through. These various filter names refer to these various filter band passes. You can get narrow band filters that only let in light near the forbidden line of oxygen, O3, one of the forbidden lines of oxygen, or you can get a filter that just lets in light around H alpha. Those are narrow band filters, and the rest are broadband filters. So these are near infrared J, H, and K filter transmission curves. In this case, again, transmission is a function of wavelength. Now we're in microns, but the black is what the atmosphere lets through, with all of the lines here being from oxygen, carbon dioxide, nitrogen, water, everything that's in our atmosphere. And then the J, H, and K bands are as shown. So they are well matched to these tiny windows in the transmission curves from, through the atmosphere. Now, the original K was longer, and the 2-mass K is called K short because it stops before all of this fuzz. I don't know for sure, but I am pretty sure that this fuzz comes from water. So if you have varying amounts of water in your atmosphere, which pretty much every place does, that side of the K-band filter is going to be variably affected from night to night, which is why you have a K-short filter to begin with. These are the 4 wise bands. Again, this is now response. Can also think of it as transmission as a function of wavelength. Wise 1, 2, 3, and 4. Wise 1 is 3.4, wise 2 is 4.6. You can see why that effective wavelength is what it is. This is 12 microns. You can see its effective wavelength right in the middle, and that is 22 microns. Now, those are rather far from being top hat functions. So is this one. So that kind of matters in how the thing is calibrated and how we use the photometry that comes out. These are some of the IRAC filters. This time it's in a little different parameter space because this is actually from a completely separate conversation talking about something else, but it was the best I could find. So this is actually energy, not transmission, as a function of wavelength, but that energy axis really only refers to those 2 white lines. This, I believe, is some kind of scaled transmission curves for the 4 IRAC colors, but I don't know what the y-axis means for those transmission curves. I'm pretty sure that they are all scaled because I am pretty sure that 8 microns is not more sensitive than the 3.5, 4.5, 5.8, and 8 microns. But there you see again the effective wavelengths are near the middle of the distribution. So this is just another view of the same concept. So here we have power as a function of wavelength, and now we're back into nanometers. Technically speaking, this is reflection and not transmission, because what this person did is they have some kind of a device that graphic artists apparently have where you can put a sample of something in the device and it will tell you exactly what color it is. And part of how it does that is it looks at the reflected light as a function of wavelength. So what this guy did was he took an entire box of Crayola crayons and stuck them in, and this is the result. So here, this is white. You can barely see it, but you see it looks kind of like the clear filter because, white light is all the colors. So that's the white crayon. Now, all of this collection here are the reds. They all are bright in the long wavelengths and then fall off to almost nothing in the blues. The greens sort of lower in the reds, come up in the green, and then go down in the blue. Then all the blues here have very little red and come up in the blue side. So it's the same idea. It's not quite the same, but it's the same idea. And this is just another representation of this. Here, apparently now you can get spectrographs for your iPhone. It's insanely expensive, but oh my gosh, I would have so much fun with it for at least a week. This is a friend of mine who used to work for the International Dark Sky Association, so he borrowed this device because he is very keenly interested in light from pressurized sodium lights versus LED lights and the whole issue of light pollution. So here we have, again, relative intensity is a function of wavelength, and this is a spectrum that it gave him looking at his orange lava lamp. So not surprisingly, very little blues and purples, some greens, mostly orange, and a fall off by the time you get to the longer wavelengths. And then this is, of course, why he had the device in the first place, because he was speaking to the larger issues of light pollution. And so you have here the spectrum of a low pressure sodium street light, where you see there's no light except for this very narrow window, and it falls off again. And this is a narrow band amber LED. And his point was that these two are very similar. So if you'd want to not contribute to light pollution, rather than just putting in a white light LED, you should put in a narrow band amber LED. So hopefully this sort of gives the bigger picture together of how filters are supposed to work. I mean, this is what I was trying to show you last night on the phone, where you have transmission as a function of wavelength and all of the filters sort of shown there. One other thing that you might be interested in is this particular page from the Cool Wiki. So I'll explain about 0 points when we get there. We're going to be converting back and forth from magnitudes to flux densities and back again. But the important bit here is that that's got the wavelength, the central effective wavelength of all of these band passes. So JH and K, the Spitzer, IRAC, and MIPS bands, the WISE bands, UBV Johnson, R and I cousins, Sloan bands, UKIDS bands, IFAS bands, Denis bands, the Akari, I think FIS, no, IRC. These are the IRC bands for Akari, the bands for IRAS, and the bands for MSX. So teams in the past from NITARP have used all of these different kinds of instruments, but look at the wavelengths. It's all in microns. So JH and K, 1 to 2 microns, Spitzer, 3 to 160 microns, WISE, 3 to 22 microns. The optical UBVRI is 0.3 to 0.8 microns, and the Sloan bands you were asking about last night is 0.29 to 0.91 angstroms. UKIDS is near IR, so 0.9 to 2. IFAS is all optical. It centers, and it's also got a narrowband wavelength, so that narrowband filter, so that's the H-alpha filter, and it's also got a modified Sloan R&I. So you get the idea. All of these are the wavelengths of all those various band passes, the effective wavelengths of all of those band passes for all of the filters that we might come in contact with.